Good morning, everyone. This is Julie McDonald with Microcom Technologies, and I'd like to thank all of you for attending today's webinar with IgniteNet. Today's host is Dan Kazwara, and he is their field application engineer, and he'll be presenting today. If anyone has any questions, please submit them in the question box, and Dan will answer them at the end of today's presentation. Dan, thank you so much for being with us today. I am finished for now. Please go ahead and take it on over.
All right, thank you, Julie, and thank you for having me today. Okay, today I'm going to have a presentation about 60 gigahertz. So I called it Let's Talk 60 gigahertz. Okay, so some of the things I want to cover is, is 60 gigahertz safe? Some people ask that question. The pros and cons of 60 gigahertz, overview of 60 gigahertz at 802.11 AD and AY, factors that limit the distance of 60 gigahertz, and what ways we have to overcome these distance limitations, and the future of 60 gigahertz, and then questions at the end. All right, so some people ask, is 60 gigahertz safe? Now, for some of us RF engineers, we might kind of laugh at that, but it's actually something that some people believe. I like what 60 gigahertz wireless brought up a good point. There's an example of a television station in London that's been transmitting 1,200 kilowatts or 1.2 megawatts of power for 60 years in the middle of London, right? And there's no evidence of any issues with that. You compare the output power to the average power of a 60 gigahertz radio that's well under 1 watt, actually typically around 25 milliwatts. The highest power are probably around 100 milliwatts or 20 dBm, which is virtually nothing. Also, 60 gigahertz itself is nothing new, really. It's been around long before 5G has been dreamt up in the past. Thinking that 60 gigahertz itself as the frequency itself, especially with the oxygen thing, was an issue. It had been around for many, many years before the advent of 5G. There's been a scientific study specifically addressing 60 gigahertz with no evidence of any DNA effects or anything like that. Actually, I remember taking my ham license, and the frequency, the ham band that affects humans the most actually is around, it's the 6 meter band or 50 megahertz. You can see from the chart there, the SEC limits for permissible exposure actually is the least at the frequency between 30 and 300 megahertz of all things, which you wouldn't expect, but that's what it is. The most exposure you'll get, I'd say 99% of people that you're going to get exposed to RF, it's going to come from your cell phone. The cell phone, of course, you have it on you within millimeters of you on your pocket next to your head. Also, the fact that the inverse square law, a lot of people don't know, the radio people know about that, but the majority of your power is up at a very, very close proximity. Then the power dissipates significantly at even just short distances away. So even that 1.2 megawatt transmitter a mile away would actually have less energy, say, than even, a cell phone, half a centimeter away from you, because the inverse square law, your power just drops so quickly. So if you're worried about RF, if you are, if somebody brings that and they own a cell phone, then they don't know what you're talking about, because the cell phone is the biggest enemy of that. Okay, so the pros and cons of 60 gigahertz. So of course, with every frequency, I treat it like a tool, right? You got different frequencies for different applications. Like you have a screwdriver, a wrench, it's the same thing. 60 gigahertz has its uses, and it's where it's where you use it and others where you may not. So the pros of 60 gigahertz, the frequency band is unlicensed. There's a lot of frequency space. A lot of frequency space allows for a lot of throughput, low latency, and wired-like speeds. That's its strengths. Lower hardware costs. I say that compared to other millimeter wave technologies, because it's unlicensed, they compare to 70 and 80 gig, it's much lower cost. virtually no interference, and more secure, and channel reuse is actually easier. Antennas are very small with high gain, and active beamforming is easier because of that. And small Fresnel zone, so that's some other advantages. The cons are the shorter range. It's very directional. To get good distances, you need a lot of dB gain. Very directional links mean it's harder to aim. It's truly line of sight. So you have obstructions, the signal's lost. There's no going through rooms or walls. It's truly a line of sight communication. Its signal is affected by oxygen and weather. And it's limited channel width options and modulation types. The standard AD and AY is pretty much what 60 gigahertz has now become, and there's not a whole lot of options there. The 60 gigahertz hardware is lower cost alternative to millimeter wave. So 60 gigahertz has been around for many years, actually, as far as I know, unlicensed in the US since 2001, and there's been manufacturers doing 60 gigahertz, but it wasn't until the Y-Gig chip, the 8211 AD chip, that really 60 gigahertz became a little more popular. And IgniteNet being the first to adopt the 8211 AD chipset, but others would follow. The lower cost chips made it a real alternative to using, say, the 5 gigahertz band, because now it's priced around the same, in lines with 5 gigahertz equipment. The next gen chips are the AY, and they are also going to be at the kind of similar price points as the AD stuff. So you enjoy some of the benefits of the AD price points in the AY product. To add to it, Facebook's Telegraph project added a big boost to the interest 60 gigahertz, which that's why you'll see now a lot more manufacturers of chipsets and manufacturers of radios to make the 60 gigahertz radios. You'll see a lot more choices coming, and the price to performance ratios are just going to get better and better over time, which is kind of what you'd expect with technology anyway. Okay, so let's go over the 60 gigahertz spectrum itself. Okay, so I said it was huge. So how huge is it? Okay, so it's unlicensed. In the US, we have a lot of space. We have actually 14 gigahertz. It was 7, now they gave us 7 more. So we got 57 to 71 gigahertz of frequency space. So it's not really even just 60 gigahertz. It's part of in the 50s, and it's all the way up into the 70 gigahertz range. Even in other parts of the world, they still have, at least, it looks like in most cases, at least 3 channels to work with. We have 6 here in the US. Now, to give you an idea of how much frequency space it is, and the big thing now is, Wi-Fi 6E had come out, and coming out right, very soon. You got 1,200 megahertz of extra space, which is huge, right? But one of the AD channels, the 2.16 gigahertz wide channel, has more bandwidth than all of 900, 2.45, and Wi-Fi 6E combined. Okay, that doesn't even add up to the 2.16 gigahertz of one of these channels. That's how wide of a channel we're dealing with 60 gigahertz. And with ultra wide channels means a lot of bandwidth. Now with AD and even AY, the modulation complexities are pretty low. Actually, the MCS12, the highest rate, is still using only 16 QAM. But because the bandwidth's so wide, the RF bandwidth's so wide of 2.16 gigahertz wide, and if you look at we're talking 27 times wider than an 80 megahertz 5 gigahertz channel. That's how much wider it is. That even with the only 16 QAM, the data rate, and that's the PHY rate, not the throughput, but the PHY rate is 4.62 gigabits. So even in the half channel mode, which the Metrolink product does support, you'll still get 2.31 or 2310 megabits of MCS12 speed, even in half channel mode. And if you in the future with the Telegraph product, there's going to be support for channel bonding, and channel bonding puts 2 channels together, 4.32 gigahertz of channel width, or I'm sorry, of channel width, gives you an MCS rate 12 speed of 9.24 gigabits. So that's a lot of speed. And again, that's still just using 16 QAM. I'm not really sure why they didn't go with higher modulation versus going with wider channels. I mean, I would think I'm not sure why exactly. I remember when they were talking about AY beforehand, when they actually had chipsets in the past, they were talking about higher modulations and using other ways of doing it. And there was mention of channel bonding, but looks like the chipset manufacturer just went with channel bonding and TDMA versus OFDM, carrier sense, multiple axis collision avoidance, and then switching over to TDMA with AY. So it's kind of what happened from AD to AY, but I digress. So the typical aggregate throughput, people ask, okay, so what is because there's overhead, what is the actual throughput? So with 4.62 gigabits, the typical you can see up to around 3 gigabits of aggregate. That means both directions of throughput with normal channel width, the 2.16 gigahertz of channel width. And with channel bonding, the testing with the Teragraph product, it's around 5.5 gigabits of aggregate throughput. Now with the shorter range, there's some advantages. Now people say there's it's always a negative to have shorter range. Actually, it depends. Because it has shorter range and is absorbed by oxygen, you could actually design your networks on purpose to be, let's say, on channel 2 and have less range on purpose. That'd be a really good design. Let's say if you're having, let's say, some close stations to each other, you'd purposely put it on a channel that has more attenuation, let's say, aside from turning down power. The free space path loss, even if you go to the higher channels, is still very high at 60 gigahertz. So any real distance, if you want to get more than, say, half a kilometer or more, you're pretty much going to have to go with very narrow directional point-to-point links in order to get, say, several kilometers. And when you do so, you pretty much reduce the amount of interference you're going to expose the area to, because you're forced to go very directional. Now, point-to-point, now, in this example here, you can see the little circles here. Imagine that's a point-to-multipoint application where you got an omnidirectional base station in the middle. And frequency reuse is real easy. What you could do is, say, figure all the client stations are pointed back at the base station. So they're very directional themselves. It requires a very high gain client to point back at the base station. And so they're all pointed to the center. The base station is using, say, a 120-degree sector. The Omni, it would use 3 of those and get 360 degrees. Wouldn't propagate much past the 500-meter radius. So you could put these close to each other and deploy them with this in mind. Actually, that's the way these 60 gigahertz networks are designed, with that in mind. So in like urban deployments, very dense areas, you could have these cells, these let's say they're kind of like 500-meter radius cells that cover these areas. So the other thing you could do with 60 gigahertz is augment your 5 gigahertz network, where you can't use 5 gigahertz, not really doing well because of all the interference, or that you need higher throughputs, where 5 gigahertz just simply doesn't cut it, and you could partially augment or eventually switch over. It kind of depends. Some people want, say, gigabit to the home, and then 60 gigahertz is a solution for that. Okay, next I'm going to cover the effects, things that affect the distance of 60 gigahertz. So there's several things. The first one I want to cover is that the Fresnel zone. This doesn't really affect distance, but it does affect, let's say, the design, and it's a positive. Is that the Fresnel zone is very small for 60 gigahertz. So compared to lower frequencies, the Fresnel zone is much smaller. What is the Fresnel zone? It's that clearance you need from your point-to-point link. So no obstructions in between your link. It's not just line of sight, but it's also including the Fresnel zone. So 60 gigahertz being such high frequency, the Fresnel zone is very small. That's a nice advantage of 60 gigahertz compared to lower frequencies. So the one big factor is free space path loss. There's all this talk about oxygen, but actually free space path loss is much higher because it's much higher frequency. All else being equal, compared to 5 gigahertz, it's about 20 dB worse. 20 dB higher free space path loss. At any given distance, it's always going to be about 20 dB higher. So it's not proportional to distance. I mean, it increases with distance, but the difference between, say, I'm using 5 gigahertz as an example, there's about a 20 dB difference. It's always going to be 20 dB higher with 60 gigahertz. The next one's oxygen absorption. Okay, now 60 gigahertz, you always hear about oxygen absorption. I always hear about, oh, it's so bad, oxygen absorption. Well, yes and no. It's actually not the biggest factor for attenuation. That's kind of a myth. It's not true. There's another factor that is worse. That's a bigger factor, which I'll cover next. But you can see at shorter distances, like say 100 meters, it's negligible. It's irrelevant. It doesn't even matter what channel you have. I know there's new interest in getting channel 5 and 6, but at short distance, it's irrelevant. You know, even the worst channel, channel 2, where the most amount of oxygen absorption is, it's only 1.6 dB. It's 16 dB per kilometer. So yeah, it's true. If you want to go more than 1 kilometer, you're not going to want to use channel 2. And for point to multi-point, your distances are typically 500 meters or less. So it doesn't really add up to much yet. Yeah, it's 8 dB, but even 8 dB is tolerable. As you get further out though, like 3 kilometers, 5 kilometers, then you could see the numbers get really bad on the lower channels, which could be a good thing. Again, like I said, for channel reuse, it's really good. So if you want to go point to point, yeah, you definitely, and go further distances, like say 5 kilometers, then channel 5 and 6 really do much better. But the problem with those is there's another even worse attenuator, and that's rain. So regardless if you have channel 5 and 6 as an option, you have to factor in rain, which is a greater attenuator than the oxygen would ever be. So with 1 inch of rain at say 5 kilometers, you got 50 dB of attenuation, assuming you know, about 10 dB per kilometer, and that's way more than oxygen is. So you think you're winning with channel going to 5 or 6, but you still got your enemy of rain, which is a bigger factor than even oxygen is. So the thing is, with oxygen, at least you could predict and calculate the amount of attenuation, but the amount of attenuation with rain, it does vary. You actually have to factor in them both, because oxygen doesn't go away unless you use the higher upper channels. Use, let's say, channel 4, it's not as bad, but when you add them two together, you can see that at further distances you still have a problem, and you add them together, it's negligible, but you put them together, it's a lot. And at shorter distances, it's negligible combined. See, at 100 meters, rain doesn't add up to too much because it's such a short link. 100-meter link is very little affected by rain because, you know, it's 1/10 of a kilometer if you think about it. So the amount of rain just doesn't add up to very much. Even at 500 meters, it's not too bad. So point to multi-point links, like say for our Omni out to 500 meters, isn't really all that affected by rain that much. You definitely want to design with signal margin in mind, but it's those further point-to-point links that really are affected. And if you're going to go any further than, say, a kilometer or more, you have to design where a 5 gigahertz failover or a lower frequency failover is in mind. That's what you should design for in those cases. Now here's a kind of an example where we're talking about margin. So let's say you got a link at, you were able to get a link at -45 dBm, and you had, say, 23 dB of margin. So that's, figure you go back here, 23 dB, you don't have any margin at further distances, but you have enough, say, even on channel 2 at 500 meters, let's say, if you have a -45 link. People ask, well, why is it so? Well, MCS1 is 68. You can't really have, that's your minimum signal to have a link, is actually 68. And people ask, well, why is it so high? Compared to 5 gigahertz, it's like -95. Well, the channel width is so much wider with actually 60 gigahertz that your noise floor is much lower. Your thermal noise floor is -81 with such a wide channel. It's actually 100 times wider channel width than a 20 megahertz wide channel on 5 gigahertz, and that results in 20 dB more higher noise floor accordingly. Well, the MCS1 is the minimum connection to connect at all. You wouldn't want to be connected to the MCS1, but figure that's after that, you lost your link entirely. So the signal margin you'd want to have it should be at least 20 dB or more. IgniteNet has the LinkPath tool. I just want to remind you, on our cloud, it's free, and it does factor in rain. You can see there in the bottom there, expected RSSI with rain and without. So you always want to design for worst case scenario. So you could put in the rain zone. And you can see the map. It's hard to read, or see that, but that's a world map, and behind it say like rain zone K. You're in rain zone K. You put in the your rain zone. It'll add in the rain rate, millimeters per hour, worst case scenario. Now, some people design it and accept that there'll be some 5 gigahertz failover, and some people don't want to have any failover at all on 5 gigahertz, and therefore everything has to shrink down a little bit. You know, even point to multi-point, you wouldn't want to be right on the outer edges. In my example before, you'd want to be in the -40 dBms to kind of have that signal margin enough to where there is some rain fade, you'd still be connected. So we got more free space path loss, we got higher noise floor, we got rain, we got oxygen. You know, there's a lot of limiting factors, say for 60, right? So what are ways that we can do to improve it, to make up for that? And because of the small wavelength, being it's only it's 5 millimeters, it's a very small wavelength, means real small antennas, which allows for a lot of dB gain, whether it be from a passive like parabolic dish type antenna, just even though it's let's say a foot diameter dish has around 40 dB gain for 60 gigahertz. So it's awesome. You got a ton of gain. The antennas aren't that big. The other thing is phase antenna arrays. So like a 1-inch square phase antenna array that does beamforming can get you nearly 25 dB gain. That type of phased arrays that you see there in the picture, that square, is what is in the BF18 and in the Omni, and also in the EdgeCore Telegraph MLTG 360 and CNs. For point to multi-point, and the reason why you don't just use a passive sector antenna is because there's just simply not enough dB gain. You're not going to get the distances. So for point to multi-point applications, a phased array antenna is used, and on the other side, a directional parabolic type antenna is pointed back at them with higher gain, like our 35 centimeter ML1, say 6035, the 42 dB gain, and point back at it, get the best distances. For point to point, you could have 2 of those dish antennas pointed at each other. And speaking of these directional antennas, so how directional are we talking about? 1 degree, and people have dealt with, say, 5 gigahertz, and you switch over to 60. It's kind of an awakening, like, wow, this stuff is really directional. So 42 dB gain, or 1 degree beam width, is, imagine a mile. You're pointed a mile, and you could be plus or minus 46 feet up or down, left or right. So you can see in the drawing there on the right, you could only be 92 feet off from left to right before you start your 3 dB down point of your signal, and it drops really quickly because it's very directional. So it makes it harder to aim. So that's what like alignment tools such as the alignment scope is really helpful. It really is a must. You mount it on the radio and get it to where it's enough to get a link on 60, and then you could fine tune it based on RSSI after that. And it's so directional that I've had a case where a guy was on like a Roan 25G, and he was only at like 25 feet, but it wasn't guy wired. It was only at 25 feet or so. He's up there putting up the ML1 6035, 35 centimeter antenna, and he'd climb up there, get it fine tuned, then he'd step down a few feet, and then his weight on the tower was enough to move it more than 1 degree. So, and you can see if it's on a, let's say it's on a pole that say moves a little bit in the wind or something, that's another problem because it's 1 degree of beam width. So very, very directional. Okay, so beamforming is another way. So, and the reason for beamforming is a mix-up for the path losses. So actually, part of 802.11ad and AY is in the protocol itself. It's called DMG, is directional multi-gigabit. It was actually built into the main protocols, the sounding frames, to take in consideration to have beamforming in mind. That was part of the beginning of when they designed AD and AY. They knew actually that 60 gigahertz propagation was going to be short range, and to make up for the losses, all those losses I mentioned, at least you could make up some of it with beamforming. So what are the advantages of beamforming? So let's compare. Okay, so a regular, and I kind of looked this up, I forget what the gain is of its standard, like a kind of 120 degree by 30 degree sector antenna. And they're out there in the market. They're around 10 dBi for that, or a 90 degree by 30 would probably have around 11 or 12 dB gain. Compare that to the BF18 Omni, it's 120 degree by about 35 degrees vertical and it has 18. So how does it have more dB gain? Well, it turns out it's got discrete beams. It scans across 120, actually 160 degrees. But the beam when talking to a client is narrowed. So therefore it has more gain, it has 18 dB gain. But you get the advantage of having a wider sector antenna, but you get the, so you have that, but you also have the advantage of having more dB gain talking to particular clients. So, and you can do that with the phased array because the wavelength's so small, you can actually do this. It's actually physically more possible because the antennas aren't too big because the wavelength's so small, and also cost effective because it's not a lot of hardware needed. The EdgeCore MLTG360 antenna actually, so that one's even more impressive. It's 90 degree by 45, but has 28 dB gain, a lot more antenna tiles in there. And I forget the beam itself, how narrow it is, but I think it's down to like 4 or 5 degrees talking to a client. It's very narrow. So, and people ask about this sector position on the Omni and BF18 radios. So I'll kind of cover that a little bit. So how it works is you got different beams. The BF18 and Omni have the 32 discrete beams in 5 degree intervals. There's actually 32 times 5 is 160. So why is it a 120 degree antenna? Well, the reason why it's called 120 degree antenna is because that's its negative 3 dB down points, but it actually scans plus and minus out to 80 degrees, so 160. Now, if you go out to say more than say plus 60, let's say you're out to 80, you're going to be down about 4 or 5, 6 dB down from center. So it's not as ideal, but you still can link and connect. You just want to be maybe a little bit closer. If you're on an Omni and you're, let's say, at sector position and it says 80, you're on the wrong sector. You should be on the next sector at 40 or minus 40. That's kind of telling you, because figure plus and minus 60 is going to be your 120. So the actual beamform beam width of the signal talking to the client is 10 degrees wide, and it's a fixed 35 degrees vertical. It's interesting, but so you have 10 degree, you could move them. There's 32 of them that are 5, you can move them 5 degrees, but the width of the signal itself is 10 degrees wide. So it's a little bit, maybe a lot to grasp, but that's kind of what's going on. So, and this is all happening because it's getting the dB gain up to make up for the losses of 60 gigahertz. With this technology, it allows for having a 120 degree sector antenna that could then have a 42 dBi client radio pointed back at it and get up to a half a kilometer, 500 meters in point to multi-point. Another way to deal with these losses, especially with rain, is just to have a 5 gigahertz failover. So the Metrolink product line has all built-in 5 gigahertz failover radio in the radio itself, and they run simultaneously. Now, people are concerned about interference, say unnecessary interference on 5 gigahertz. The radio is just passively connected, if you will. There's no traffic being passed until the 60 gigahertz radio goes down. But if it goes down, then it's nearly a seamless transition because it's already linked. So you got them both linked at the same time. And then say 60 goes down, there's a severe storm or something really makes the link drop temporarily. At least you're still up. And I'll tell you, as you guys know, WISPs out there, you know that slow is not as bad as down. So that's kind of the deal. Some people really push the limits of the distances and then just are okay with the 5 gigahertz radio failover. And some people actually use only the 5 gigahertz where non-line of sight 60 sometimes is, like say you got an Omni, there's no reason you couldn't just connect a few of them only on 5 gigahertz if there was a non-line of sight scenario with a few of the, let's say, homes in a rural application. Some people ask about the future. Okay, this is kind of maybe my opinion a little bit. It's really hard to get information on 60 gigahertz, I'll tell you. So I've seen already that there's going to be channel bonding. That's already kind of in the works there with the Qualcomm 8211AY chipset. That's a given. We're gonna get channel bonding. So that's something that's already happening. Even more channel bonding, maybe, I don't know, but at least with 2 channels. Higher client counts per AP. So AD, the standard and the chipset really called for 8 to 1 point to multipoint. The Metrolink, we pushed it. It could support 12. I remember originally we mentioned 16, but reliably it's 12. So 12 to 1 with point to multipoint. Now with the AY and using TDMA, it's 15. And that may increase in the future with other chipsets. I don't know, but I expect that to be increasing in the future. It's already increased to 15. More radios that support channel 5 and 6. This is more for like further maybe point-to-point stuff. It really doesn't have that much, like I said, I mentioned it, below half a kilometer or point-to-multipoint, not that big of an advantage. Again, rain is your bigger enemy anyway. More radios with active beamforming on the like point-to-point. So for example, we're working on coming out with a long-range version of the client node for the Terragraph. The Terragraph. It's going to be similar to the 35 centimeter 42 dBi radio, like the ML1 6035. But what's going to be different? It's going to have active beamforming in it, so it'll have 40 to 42 dBi, but it won't be 1 degree beam width. It's actually going to be around 3 degrees of beam width, and so it'll be still pretty directional, but it'll active beamform down to 1 degree. So at least alignment's easier and it's more forgiving when it comes to, say, a little bit of movement. So it aids. It's going to be easier. It's easier to align 3 degrees than it is 1 degree. I'll take that. I'll take anything. The more radios that will support or have faster uplink, the connection speeds, the Ethernet or SFP. You're gonna see more 2.5, 5 gig. You're gonna see more SFP plus type radios. That's what I predict, because the bottleneck you can see is not necessarily even the wireless. It's the it's your connection to the radio itself could be a bottleneck, especially with channel bonding and other future tech developments. That could be a bottleneck. So you're gonna see more radios come with that. Just in general, you're going to see more manufacturers making the chips. You're going to see more radio manufacturers in general, I think, joining on board with doing 60 gigahertz, and therefore you'll have better price to performance ratios. I mean, of course, that's with technology always increase, but I think it's going to accelerate. I think 60 gigahertz ADAY kind of was at a standstill. It's like the development wasn't really that fast-paced or changing, but I see it now really accelerating. And I see more countries freeing up 60 gigahertz space. I mean, it's not so much an issue here in the US, but because of Facebook, Terragraph, they're going to push other countries that, let's say, don't have allocation or not a lot of frequency space to then add more frequency space for it. Another thing is, I think there'll be some more interest in passive reflectors for millimeter wave. I see a little bit of interest. I think there might be more as time goes by. That might be a little early for that, but they even make paint, I think is that you could paint on a wall that could reflect millimeter waves. think it's more for 5G stuff, like 28, 39 gigahertz, but there's talking about why wouldn't it, they could make it up to work up on 60 gigahertz also. And because of beamforming, that doesn't have, it could adjust its beam to then reflect off it, and the beamforming could then adjust its beam direction accordingly to get the link. So it's interesting. It's you don't have to worry about trying to figure out the angle. It'll do it for you. And that is it for my presentation. Julie, I'll let you take it over and see if there's any questions.
Thank you so much, Dan, for that presentation. I greatly appreciate it. And yes, I do have some questions for you. Let's take a look here. First question. Will IgniteNet focus more on 60 gigahertz devices?
Well, there is the Teragraph. The focus is currently, well, it's both. I mean, it's EdgeCore. EdgeCore, IgniteNet are the same company. EdgeCore owns IgniteNet. And you'll see kind of a wide variety, you'll see switches, you're going to see indoor, outdoor APs, like the new EAP 101 and 102 are indoor APs under the EdgeCore name. The Teragraph product is actually under the EdgeCore name. The new products are the Teragraph, it's under the EdgeCore name. The MLTG 360 and the CN. The new one coming out in the next couple months or so, we're going to have a long-range version, I mentioned it, of the CN, so for point to multi-point. So that's going to be, I think, a game changer for us, because it then really it's a viable, real replacement for our Metrolink product. See, the Teragraph didn't have a long-range, we don't have a long-range client radio yet. For the Teragraph. The Teragraph CN can go about 100, 150 meters back to the 360 base station, compared to the Metrolink, which does about 500 meters if you use the 42 dBi client pointing back at the base station. You can get about 500 meters. So that's the Metrolink. We don't have a 500 meter equivalent yet for the Teragraph product line, the AY product line, and we will in the next few months. So that, look out for that. I think that's the big one that in the near future to look out for.
Thank you very much, Dan. Next question here for you. What is the backup for the 60 gigahertz units?
The radio in there is a traditional 802.11 AC 2x2 wave 2 radio in there. That's what's used for the 5 gigahertz radio to do the failover.
Thank you so much. Next question here. I think it's a follow-up to the one I just asked. Can these units be used in Ptmp modes or just bridges?
Yes, for example, the client radio, so those very directionals, you would do that point to point. So I'll give you an example. The ML1 6035 or the ML 2.5 6035 is our directional client, but it could also be point to point. So one acts as a client, the other one acts as an access point, if you will. It's just point to point. Put one in master mode, the other one in client mode. They talk to each other. So the clients can either be either or. Typically, they're used to talk to a point to multi-point base station like the Omni or the BF18, but they can certainly talk point to point to each other as well as clients to each other as a point to point application at further distances too, because they're both, higher gain. They're both very high gain. So you could actually get a few kilometers pointed directly at each other.
Thank you for that, Dan. Next question here for you. Are IgniteNet units IP67 rated?
No, they're not IP67. I'm trying to remember their IP rating. I think they're IP55.
Thank you. Next question. Is the link calculation tool free?
Yes. Yeah, great question. Yeah, just go to cloud.ignitenet.com. The cloud itself is free too. We actually expanded the amount of devices that can be managed on the cloud for free from 2 to 50. So that's a new addition. Creating the cloud account is free. You can create the account just to use the tool if you want. the LinkPath tool is free to use, and the cloud is free to use even for devices up to 50 devices.
Excellent. Thank you, Dan. Next question here for you. What device band and IgniteNet device would you recommend if there's no line in sight from 1 to 5 kilometers?
Well, depends on how severely obstructed you're talking about. Then it would be you'd have to use 5 gigahertz. You could use our ML16035. The 35 had, okay, so I mentioned it has 42 dB gain on 60 gigahertz. It has 22 dB gain on 5 gigahertz. Those are still pretty good gain. So we don't really have a 5 gigahertz only radio that would be that directional. So point to point, 22 dBi antennas pointed at each other would be your best bet at 5 gigahertz. But if it's truly non-line of sight, then 5 gigahertz, no matter who you use, doesn't matter if it's us or anyone else, it wouldn't matter. 5 gigahertz has its limitations. If it's not line of sight, there's obstructions that are just too severe, then you may have to look at other options than even the 5 gigahertz band that we don't do below 5 gigahertz. So maybe a 900 megahertz could be an option possibly, but we don't do that.
Thank you for that, Dan. Next question here. Will IgniteNet go for Wi-Fi 6 as well?
Yeah, actually Wi-Fi 6 is out already. The EAP 101 and 102 are 2x2 and 4x4 indoor APs. So that's what we have for Wi-Fi 6 already, and there's more coming.
Great, thank you. Next question. Regarding link profile and link coverage, is this a subscription based or one of a payment use or a one-time payment use?
Okay, there was within our cloud LinkPath called another optional feature called LinkPath Pro. LinkPath Pro is no longer available and no longer supported. That one actually did topographical predictions of coverage. We don't, that feature is no longer available in the LinkPath Pro. That was a paid type application, so it's no longer available. I think your best bet would be use your LinkPath tool to calculate your paths and your distance, based on your distances, and then you could still do it. You just have to, Google Earth and do it that way. But yeah, as far as the tool was kind of limited and had some issues, so we kind of just moved to just doing LinkPath only and no longer supporting LinkPath Pro.
Dan, thank you so much for answering all of those questions for us today. And also thank you to everyone attending today's webinar. And if anyone has any further questions, please feel free to contact your sales rep or email us at sales@microcomtech.com. And if you wish to view any of the products mentioned or shown today, please visit us at www.microcom.us. And please remember, this presentation has been recorded and will be uploaded to our Microcom YouTube channel so you can view it again. Thank you, Dan, for your time and very interesting information today. We appreciate it. Thank you. And until next time, have a fantastic day, everybody.